to make sure that we moved along a little faster than I would have liked towards the second part of the lecture. That tends to happen as you get closer to finishing. You have this innate desire to get stuff done, which is not a good thing. So, if at any point you feel like you haven't grasped, just tell me and I'll kind of slow it down. Okay. So, or if you're not comfortable, just come during the coffee break and say, hey, can we go through this again? I think the goal is not to finish all the material, but just to make sure that we convey the important aspects in a clear and comprehensive fashion. Okay. So today what we're going to do, so if you think about what we did yesterday, was we spent a lot of time trying to, after the introduction, trying to look at a variety of models and assess how they actually lead to a class of variational problems, whether they're VIs, complementarity problems, or MPECs, or even more generally multi-leader, multi-follower games. So today we're going to look at the most fundamental object in all of these, which is the variational inequality problem. Now just to remind you again, the variational inequality problem in its, and I want to give you, I don't always have, I have some pictures regarding the VI later maybe, but just to remind you, so VI XF is the problem that we're going to be focusing on. This problem requires an X such that Y minus X transpose F of X. Oh, I forgot. Oh, I apologize, sorry.
I hear some sound, but it's like far away.
Okay. For all Y and X, okay, and just to make sure you understand what this looks like, if I gave you a closed and convex set, suppose I gave you this set, just some set. This is the set X. I'm interested in a vector X such that, if you're at this point, suppose the mapping points in, this is negative F, this is F of X, this is any Y, and you want to make sure that all angles are acute. Okay, so that's what you're looking for. You're looking for an X such that if you pick any vector Y in the set and you consider the acute angle between Y minus X and that vector F of X, you'd like to make sure that that angle is acute. The other way to look at this is using what we call the normal cone. Remember yesterday we talked about the normal cone? So the negative of F is, at this point you can construct a normal cone. Okay, it's some cone, whatever, maybe it's slightly different. But you want to make sure the other way to look at this is the negative of F of X plus the normal cone at X, 0 lies in this. So this is often called a generalized equation, and this is an equivalent representation of a VI. Okay. Now today what are we going to do? We're going to focus on providing you with tractable conditions for when such problems have solutions. Okay. And when those solutions happen to be unique. Okay. So let's start. I'm going to start with the simplest problem that leads to a VI, which is a convex optimization problem. So the convex optimization problem, in this case, we're going to assume that the function is differentiable. So we're minimizing a differentiable convex function over closed and convex sets X. And so then the following holds. So this is a necessary and sufficient condition. So the term necessary and sufficient just means that an equivalent statement for the optimality of X is this condition. So X is a solution to this optimization problem if and only if X solves VI X the gradient of F. So that's the mapping. Okay. Now, in this condition does not leverage the underlying algebraic structure of X. So X could have some nasty structure within it. What I mean by nasty structure is it could comprise of hundreds of thousands of constraints. It doesn't matter. All that we require is that X itself just be closed and convex. Okay.
Do we impose closed and convexness?
Pardon?
Do we impose
Closed and convex, yeah. So, so this is for necessity and sufficiency. And now the reason why I start from here is this is probably the most, common. This is probably the most common instance of where a variational inequality problem arises. Okay. More generally, the variational inequality problem requires an X such that y minus x transpose f of x is non-negative. Okay. Now, what I'm going to show you is that this problem subsumes convex optimization, Nash games, convex Nash games, traffic equilibrium problems, some subclass of those, economic equilibrium problems, Walrasian equilibrium problems, a host of problems. And there are, other settings that also emerge where you can use variational inequality problems to capture the underlying solution set.
That's good.
Yes.
Are there any special properties when the angle is 90 degrees or when this equality holds?
So when the equality holds, so the standard one that at least I can think of is when f of x is equal to 0, which is the equation solving problem. So it's not that the angle is 90 degrees, it's when f of x is equal to 0. So when f of x is equal to 0, that's basically solving a system of nonlinear equations. So that is a generalization of solving the stationarity conditions of any optimization problem, not just convex, right? Any optimization problem. Okay. So now I'm going to provide you with some equivalent formulations of EIXF. I want to make sure you understand why I want to provide you with equivalent formulations. The key reason why I'm interested in providing with equivalent formulations is when I try and provide you with an existence statement, the way we're going to develop the existence statement is using what we call fixed point theory. Okay, so a fixed point of a map, if I gave you a map that goes from Rn to Rn, the fixed point of a map is an x such that x is equal to f of x. Okay. This is equivalent to saying g of x equals 0, where g of x is f of x minus x. Okay. So the root finding problem, this is the root finding problem or system of nonlinear equations, and is equivalent to the fixed point problem. My goal is to show you that this problem is equivalent to this problem for a particular choice, not for the same f, some other f. And once I do that, I'm going to develop, using degree theory, a fixed point theory for this. Now, I could directly leverage fixed point theory, but one of my goals in this class is to at least expose you to the theoretical foundations for how we apply these techniques. Okay? Because if you go out, you want to make sure you apply these results. Sometimes the results are not in a form that you can apply. So I may take you up on that, Jalal, later. It looks like this keeps doing it. If it does it once more, maybe you can log in.
Do it now or?
No, we'll see. Hopefully it doesn't. I mean, actually what I could do is I could just turn off Wi-Fi. That's probably the better thing to do. Okay, so now crucial to solving or to stating this problem as a fixed point problem is the need to articulate the notion of a projection. Okay, so the projection onto a closed and convex set is basically a point, the closest point to a point which you're trying to project onto the set. Okay, so when that set is convex, then that projection is unique. Okay, now you can look at it and conclude or try and somehow surmise that it's unique, but there's another way to immediately show that this problem is unique. So one of the things, yesterday, I think by the time we reach 4, it gets tiring to have exercises. So today what I decided was we slow it down, but we spend some time along the way trying to prove some results which sometimes I might take for granted. Okay, I think that's a better use. And by the time we reach around 4, it's better to code at that time because everybody's mind is a bit short, mine particularly. So let's look at this problem. So this is minimize. So this is the projection problem. Given an x hat, I want to find a y that is closest to x hat and y has to lie in x. Okay, so before I progress, I want to make sure that everybody understands that this is exactly what this problem states. This is also denoted by pi of x on x hat. So pi just means large pi, or uppercase pi, just means projecting x hat onto the set x. Okay, Christy? That clear? Alicia? Clear? Okay, so then the question that I have is why does this lead to a unique solution? Okay, the reason it leads to a unique solution, so let me ask you more generally. In convex optimization problems, does anyone know when unique solutions emerge? If you solve a convex optimization problem, under what conditions do you have a unique solution? Well, the condition is that the function has to be strongly convex. Okay? So what is a strongly convex function? In the quadratic case, so a function f is said to be strongly convex if, so I'm going to assume the function is a C2 function, a twice continuously differentiable function. If the Hessian of the function, and there are other representations when it's just once differentiable, or not even, it's, so what this means is that the smallest eigenvalue of this Hessian matrix is n, whatever x might be. Okay. So now, if for some m greater than 0. Okay. So now, if you look at this problem, what is the function in y? It's y transpose y minus twice x hat transpose y plus x hat transpose x hat. Okay. Now, if you differentiate it twice, what do you get? You get the identity, twice the identity. Okay. So this problem always provides you with a unique solution. Okay. Now, can someone tell me what would happen if you had a non-convex set? Can you think of a case where if you're projecting onto a non-convex set, you get non-unique solutions? You think of an example where that happens. So a simple example is this. And you're in the middle of these two. Let's, maybe you're here or something. And then both of these are the closest or something like that. Okay. Okay. So now, let x hat be a vector in Rn and x be a closed and convex set. Then the following hold. For each x hat, the projection exists and is unique. How do I get that? I get that from convex optimization theory. This optimization problem always has a solution, and that solution is always unique. Okay? So the first statement follows entirely from recasting the problem as a strongly convex optimization problem. Okay? The second point is the projection satisfies the following condition. So if you think about what this condition means, what's the first thing that strikes you about this condition? If I look at these as two vectors, y minus x hat and x hat minus x bar minus x hat. What strikes you about these two vectors? What do you think you require from these two vectors for all y? The inner product is non-negative, right? So if the inner product is non-negative and the two vectors, when is the inner product non-negative? When the vectors form what kind of angle? An acute angle, right? So now let's think about this problem. This is x, this is y, and I'm looking at, so look at x bar is this point. Okay, so this is y minus x bar. So this is y minus x bar, and this is x hat minus x bar. Okay. This class is terribly exciting. I moved to orange now. Okay? So now I have x hat minus x bar, and what you notice in the projection is that this is 90 degrees. So this angle is obtuse, and so y minus x bar and x hat minus x bar form an obtuse angle. So it's y minus x bar transpose, right? Y minus x bar transpose x hat minus x bar is less than 0. You flip this here, you can see what happens. You just get x is greater than 0. Okay? So the proof is relatively straightforward. Is this clear? Okay, so the first statement is just to make sure that we understand the properties of the projection. Okay. Now, next what I'm going to do is use that formulation, use the definition of the projection to come up with some equivalent representations. So by definition, x star solves VI XF when x star lies in, I'm sorry, that should be x, okay, not k, x. X star in k, that should be x star in x. And y minus x star transpose f of x star for all y in x. Now, if I slightly transform this, right, so what I do is, so I want to make sure you understand why this inequality is useful. So this is greater than or equal to 0. So now you have something that looks like the projection, right? So look, you have y minus x star, x star, x star, and again another vector. Okay, and remember y is to lie in x. So what you find is x star lies in x when x star is the projection of x star minus f of x star on the set x. Now why do I say that? I say that because you remember we just proved that relationship y minus x bar transpose. So I did the other one, which is x bar minus x hat is greater than or equal to 0, right? Did I screw up something? Hold on a second. Y minus x bar. Okay. So now from this, what you can see is this is what you're projecting, right? So this takes on the role of x hat, which is the, remember this is what you're projecting, x hat. So this is like x hat, and what you like is x bar is the projection of x hat, right? So if it's a projection of x hat, or now x bar in this case is x star, and the projection of x hat and x hat is x star minus f of x star. Okay. And so what we've come up to is that x star solves the variational inequality problem if and only if x star is equal to the projection of x star minus f of x star. Okay? So, again, let's take a break, make sure we understand. The reason we are trying to go along this avenue is so that we can reduce the problem to an equation, to a nonlinear equation. And once I have a nonlinear equation, I can recast it in a different form and apply fixed point arguments. Okay? So, is it clear how I reached it? The first thing I did was I wrote out the solution of a variational inequality problem. The requirement was this. I then added and subtracted x star, and then I found that it abides by the projection property. The projection property was basically, don't sit and memorize the property. Just take a set, draw a point, just make sure the angles are, obtuse or acute, whichever way you want to do it. And you'll be able to derive that property. And you immediately see, oh, look, the property holds. Yes?
The property is equivalent to a definition of the projection then.
Yes. So basically, if this holds for all y in x, it's if and only if. And the reason why it's if and only if, Arno, is because it's a convex optimization problem, a strongly convex problem. Remember how the projection property came about? It came about because you had a solution to the convex optimization problem. And you showed that for any solution, this has to hold. Right? For any solution, you had to have this obtuse angle or acute angle, whichever way you look at it. Okay? So now what I do is I say, oh, I can rewrite this mapping just as g of x star, just label it as g of x star, and I'm left with a fixed point problem. Okay? So a fixed point problem is just a problem given by h of x equals x. Okay? Okay. So now, in other words, what we have is x star is a fixed point of g. I don't know why I changed notation here, just to be g of x star. Okay, psi of x star. And this is often referred to as the natural map of the VI. There's also something called the normal map, which we won't do in this class. But the natural map is a way to assess if you're at a solution, a simple way to assess, right? If you had to assess without being told about the natural map, you would have to go and check that inequality y minus x transpose f of x holds for all y, right? And now that's impossible because there's an uncountably infinite number of y, right? So another way to do it, which is clean, is just check if this equation holds, right? If Anubhav came up with the x that he claims is a solution, just substitute in this, right? And I'm going to show you how. If you think about how do you solve this, because this is a projection. Well, just take your x, subtract f of x, project it onto this set, you get some other vector, and subtract that from x. Check if that is, I don't know, order 10 raised to minus 7. If it is, it's a reasonable approximation of a solution to a VI. Okay? Okay, so psi of x is often referred to as a natural map associated VI xf, right? So whenever I write sol, I just mean the solution set. Okay? Sol xf is the solution set of VI xf. So x solves VI xf if and only if the natural map at that point is 0. Okay? In effect, the problem of solving VI xf is equivalent to solving a non-smooth equation. Why do I call this equation a non-smooth equation? Because it has a projection inside it. So if I perturb x, the projection doesn't change smoothly. Okay? There's a jump. Okay, so now let's start trying to relate that to Nash games. Okay? So consider an n-player Nash game in which the ith player solves the parameterized convex problem. Right? You have to minimize theta I of xi given x minus I. So I want to make sure, there's a lot of notation flying around. Let's make sure everybody remembers what x minus I is. X minus I is just the rival decisions. So everything excluding xi, right? It's x1, x2, x3. If you're the 7th player, it's x1, x2 all the way to x6, and x8 all the way to xn. Okay. So this function is convex, and when I write C1, it just means continuously differentiable. right? And why do so whenever I put an assumption, your first thought should be, why has he imposed that assumption? Because what do assumptions do? Assumptions restrict the reach of the theorem, right? So if I impose a continuously differentiable assumption, you should be asking why, right? And the reason why I need it is for me to write out a variational inequality problem, I need to take a derivative. That's not the only way. You can work with non-smooth functions, but in this class we won't. Okay? So that's why I need continuously differentiable. Why do I need convex? Because I want these variational inequality problems to be necessary and sufficient conditions of optimality. If it's not convex, it's just a necessary condition. Okay, now you might say, why, so what? Well, the reason is, if you get a solution of necessary conditions, they may not be solutions of the original problem, right? There might just be some, maximizers or stationary points, who knows what, right? Xi is a closed and convex set in Rni, and the overall set, capital X, is in the larger space of x1 times x2 times x3. So this is a Cartesian product. What is a Cartesian product? Just so that you know. So whenever we look at, if I say x1 lies in x and x2 lies in x2, then the set x, the vector x, right? If you look at x1 and x2, this lies in x1 times x2. What does that mean? It just means that x is of the form x1 comma x2, where x1 lies in x1, x2 lies in x2. Sorry. Okay. Okay, so the first thing that we've done is we've taken the convex optimization problem corresponding to each player, rewritten the necessary and sufficient conditions using so all I've done is I've written x1 star is the minimizer of the parameterized optimization problem. That's just the Nash requirement, right? That at a Nash equilibrium, no player has a desire to unilaterally deviate, right? Okay, so now what I'm going to do is I'm going to rewrite this condition using a necessary and sufficient condition associated with the VI. Okay? Now what have I done here? I've written, these are the sets, the feasible regions. These are the gradients corresponding to each player's cost function, parameterized by rival decisions at the optimal equilibrium level. Okay. So why is it x1 comma x minus 1 star? Because you fixed the rival decisions at x minus 1 star, and you are allowed to optimize. And you're only at Nash if you choose to not. If you're still, if x1 star is still an optimal solution. There could be multiple optima, but you need to make sure at least that's in the solution set. Okay. So this is important. You do this for each player. Okay. So now that you have that, what you can then say is that this problem is often, now look, this is not a single variational inequality, right? I can write this. If you look at x1 star, so if you look at x1 star in the solution set of is equivalent to saying y1 minus x1 star transpose gradient of x1, x1 star, x minus 1 star is greater than 0 for all y. Okay, that's equivalent. So now if you look at these, there are n variational inequalities, not one, n. Right? Because each of these, but they're not independent, they're coupled. Right? Pardon? Gradient of theta. Oh, sorry. Okay. So now you've got n variational inequalities. So whenever you have a problem like this where you have n variational inequalities, that problem is often referred to as a Cartesian variational inequality problem. Why is it called a Cartesian variational inequality problem? Because you can reduce it to a variational inequality problem like this with a single x, where the x is a Cartesian product. Okay, it's a Cartesian product. Not all sets can be written as Cartesian products. For instance, if I gave you this set, if I gave you this constraint, suppose I said x was this set cannot be written as some set x1 times x2. On the other hand, this set right, let's say 0, 0, can be written as x1 times x2, where x1 is this set and x2 is that set. Okay, so a Cartesian set in say in 2D just means that I've got a set that I can write as this times this, and this is the whole set. Okay, but now suppose I have a set like this. That set can't be written as the Cartesian product of two sets. Okay. In fact, these are the types of sets you get when you have shared constraint games. Okay, but this is so now what you notice is you've got a Cartesian product of sets, and the mapping F is just this concatenated gradient map. Okay. Now, there's a simple result which shows that a solution, you can get a solution to this problem by solving a single variational inequality. And I want to, again, so in the interest of trying to solve some of these during the class, I thought we could go through this proof. Okay, so this is not a difficult proof, but it helps you just get a little more familiar with how these results get proven. Okay, so let's see what we're trying to prove. We're trying to show that if I get a solution to this problem, so I get an x1 star, x2 star, xn star that collectively solve this problem, then I have an x that solves this problem. Now look, this is a single variational inequality. That's a collection of variational inequalities. Okay, so let's make sure we understand that the distinction. We have n versus 1. Okay, and I want to make sure that the solution of one is exactly the solution of the other, and vice versa. Okay. Okay, so remember, whenever I try and prove a condition like this, it's an if and only if condition. So whenever I try and prove a condition which is whenever I try and prove A if and only if B, then I need to prove that A implies B, and I need to then prove that A is implied by B. Okay, I need to prove both directions. Okay, so let's prove the forward direction. So suppose Z is a solution to solve Ki, Fi, and what that means is I basically get a Z that collectively solves each of the n variational inequalities, which means Zi is a solution to Vi, Ki, Fi parametrized by Z minus I. Okay. Now, if that happens, if you look at this, what happens here is, so let me just write this out. Sometimes I take a step which so if I told you Zi lies in the solution set of is Fi there? What did I use? Yeah. Using Ki just because they use Ki. Okay. So this means that Yi minus Zi transpose Fi Zi Z minus I is greater than 0 for all yi in ki. Okay. Now, if I sum this up, now this holds for all I, right? This holds for all I. Why? Why? Because the zi lies in this for all I. So if I sum up these inequalities, then what you have is right? But that's equivalent to saying okay, because I can write this as the inner product between these two vectors. But this is just y minus z transpose fz. Okay? Which means that z lies in the solution set of here. Okay? So in one direction we've gotten it. Let's go in the other direction. The other direction is a little easier. So fix an I in. Now what do we need to show? We need to show that for any arbitrary I, if I've got a solution to vi xf, I find that zi is also an optimal solution to this vi. So I'm going to fix an arbitrary I, because for an arbitrary I this works, it works for any I that I've chosen, right? Fix an arbitrary I. If z lies in solution set of kf, then I have what? And then for the other ones, what I'm going to do is, let me show you. Okay. So we know this holds, right? This is because z lies in the solution set of kf. This is equal to y1 minus z1. Okay, this is just by opening out these. Now what I'm going to do is, remember I can choose the y's. So I'm going to choose for every y that is not, so for every yi, which is not, where I is not from the chosen I, I'm going to choose these yi's to be equal to, so yj is equal to zj, j not equal to I, which means that this reduces to what? Just yi minus zi transpose fi of zi, phi of z. Does everybody see how I've gotten from here to here? I chose these to all be equal, yi to be equal to z. So if that is 0, then those do not contribute to the overall inner product. Okay? So what I'm left with is just this inner product, but this leads to the statement regarding the solvability of vi ki fi zi z minus I. Okay? So which means that if I get a solution to vi kf, I've got a solution to vi ki fi given z minus I. Okay? Does everybody see this? If not, I'll go through it again.
Can you repeat just the last step?
Yeah, the last step. So essentially what I did was, so this holds from z lying in the solution set of kf. Okay? I just opened it out. Okay? And then what I did was, because I've picked a particular y, I've now, and remember the y's are in my control. So I need to satisfy this for all yi in ki. Right? That's what I need. So what I do is I set let yj equal to the zj for j not equal to I. And as soon as I do that, all these other products just disappear. Okay, and then I'm able to get exactly this because I'm trying to show this is non-negative. Okay, Priyanka, clear? Yes.
How can we make this assumption?
Oh, we don't make the assumption. We choose it. Because remember what we've done is we can select the yi's. So we need it to hold for all yi's in ki's. So at that point, I choose the yj's to be equal to the zj. Because what am I trying to get? This has to be, this holds, when does this hold or not? This holds for all y in K, which is the Cartesian product of ki's, right? Holds for all k. So it has to hold for y1 equals z1, y2 equals z2, and so on. Okay? Okay. Okay, so now given, okay, so I want to make sure. So now what we've done is we've shown that the variational inequality problem that corresponds to the concatenated optimality conditions of the Nash game is equivalent to a single variational inequality problem. Okay? Is that clear? Next, what I'm going to then show you is that this can also be shown to be equivalent to a complementarity problem. So let me define a complementarity problem because we've talked about it loosely yesterday. So given a cone X and a map F, the complementarity problem Cp x comma f requires an X such that this is just the reversed lies in. Okay, this is lies in. This just means X lies in X. F of X lies in X star, which is the dual cone, and X and F are perpendicular, which means component wise their product should be 0. Okay? So what is the geometric intuition of the complementarity problem? The geometric intuition is that if I gave you a set which is a cone, suppose this is X, right? Let me not write here. Right? The X star is something like this. Okay, so this is X star. Right? So I want an X it's difficult to do this because now you have to make sure these are orthogonal, but you get my idea because in different dimensions you need to make sure xi star and fi of xi star are orthogonal. See, look, when I say that x is orthogonal to f of x, it means xi star is orthogonal to fi of x star for all I, which means that essentially what you're going to have is one of these is equal to 0. Okay. So if you take these two vectors, you're going to find that they're orthogonal. Okay. Why is this important? The reason why this is important is that when we're working with, and I'll make this clear next. The reason why we're interested in complementarity problems is sometimes I have the algebraic structure of the set X. Right? It's not just an abstract set, we have the structure. So we know X is an intersection of a bunch of inequality and equality constraints. So as a consequence, when I use that within the optimality conditions, I'm left with these complementarity conditions. Okay? And you saw that yesterday. Remember, we saw complementarity conditions. So let X be a cone in Rn. Then X is a solution of VIXF if and only if X is a solution of CPXF. Okay, so this is a result by Karmardian in 63. It's a very simple result to prove, but a very important result. I think it's 65 or something, I can't remember. So if X is a cone in Rn, then X is a solution to VIXF if and only if X is a solution of CPXF. So if the variational inequality problem is specified on a cone, right? So the set X is not just a closed and convex, or not just an arbitrary set, it's a cone, right? Then X is a solution of VIXF if and only if X is a solution of CPXF. Okay, so there's a one-to-one, I mean, there's a if and only if relationship. Again, let's try and prove this. Okay, let's try and prove this. These are relatively straightforward results. They just take a little bit of work, but the more you see it, the more you get used to the machinery that goes into analyzing these problems. Again, we're trying to prove if and only if, so let's move in the forward direction. So in the forward direction, let's assume that X lies in the solution set of Vi xf. Okay, so if it's in the solution set of Vi xf, then we have that y minus x transpose f of x is non-negative for all y in x. Now, since y is an x and x is a cone, and since a cone must contain the origin, we have that 0 lies in x. Okay, let me write this out next so that you can see it. Okay, so let's do this. So we have y minus x transpose f of x for all y in x. Okay. Now since x is a cone, 0 lies in x. Right? So choose y equals 0 because it has to hold for all y, so it has to hold for y equals 0, which implies negative x transpose f of x is less than or equal to 0. Now, remember where I'm trying to go. I'm trying to go to reach here. Now let me ask you a question. If I'm trying to reach here, what I've concluded from this, is x transpose f of x is less than or equal to 0. What do I need to prove to get to x transpose x is f of x is equal to 0? Right, I need to prove that x transpose f of x is greater than or equal to 0. So what choice of f would allow me to conclude that, Priyanka? So just from here, just look here. Choose y as 2x, right? So if you choose y, and y, but what is required for us to choose y as 2x? What should 2x satisfy?
It should line the cone.
It should line the cone. Does it line the cone? Yeah, because it's a cone, right? So if x lies in the cone, since x lies in x, it implies 2x lies in x since x is a cone, right? Which implies that 2x minus x transpose f of x is equal to x transpose f of x is greater than 0, right? So by 1 and 2, so by 1 and 2, we have that x transpose f of x is equal to 0. Now we know that x lies in k. The last thing I need to show is f of x lies in k star. If I can show f of x lies in k star, then I'm done. Okay? So, how do I show that f of x lies in k star? I need to show that f of x lies in the dual cone. What is the dual cone? The dual cone, remember what the dual cone is? What do I use? X star is the set of y such that y transpose x is non-negative for all x in x. Okay, so I need to show that f of x makes an acute angle with every vector from x. Right? That's the definition of the dual cone, right? So I need to make sure that f of x transpose x is non-negative. I need to show f of x, transpose whatever y is non-negative for all y in x. Right? But what do we know? We know that it satisfies the solution property of Vi, which means y minus x transpose f of x is greater than equal to 0, which implies y minus y transpose f of x is greater than x transpose f of x. Well, what do we know about x transpose f of x? It's 0. And this holds for all y. So which means y lies in f of x. Sorry, f of x lies in x star. Okay? Is that clear? So this is a bit of a mouthful. Let's make sure that we've gotten it. So the forward direction required us to show that if x was a solution to Vi xf, x satisfied the complementarity problem. Okay? How did we show that? We needed to show that x, x was immediately in capital X. So whenever I need to show that x satisfies this, so this holds trivially because we have that x satisfies Vi. I need to show this and I need to show this. I showed this by choosing y appropriately. I chose y as 0, chose y as 2x. I could conclude that x transpose f of x was 0. The next thing I did was I just used the statement of the Vi to conclude that y transpose f of x was always greater than x transpose f of x. And x transpose f of x was 0. Okay? Anna, clear? What part is not clear? Which part? The 2x. So the question is why 2x? So the reason why 2x, so the first thing is the reason why I'm trying to bring 2x in is when I saw that I had shown this, I realized what am I trying to head towards? I'm trying to head to this. Why am I trying to head to this? Because this captures the perpendicularity relationship. But how would I claim this? The only way to claim this, if I already have negative x transpose f of x is greater than or equal to 0, is to prove that x transpose f of x is greater than or equal to 0. Because because what does this say? This says that this is less than 0. When something is less than 0 and greater than 0, then it has to be equal to 0. How do I show it's greater than or equal to 0? Well, in this relationship, if I choose y as 2x, we immediately know that you have x transpose f of x is non-negative. But for you to do that, you need to make sure 2x lies in the set. Now, if I give you an arbitrary closed and convex set, like I gave you a set like this, and I said this is x, if I take 2x, it may be outside the set. But remember, this is not an arbitrary set, it's a cone. So if I pick a point x and I scale it, it's always in the set. So 2x always works. Okay? Is that clear? Anna? So what I've done is basically I've been able to show that if a point solves Vi xf, it has to solve Cp xf when x is a cone. Not true in general, only when it's a cone. Okay? Gwen? Clear? Okay, now let's go in the other direction. So suppose I told you that x solves Cp xf. Is there some part that you're not getting? I can go through it because others might have the same question. Anything clear? Okay. Let me go through that. Let me go through that again. So the reason why that's in f of x is in x star is because. So first, why be interested in that? Because that's the third part of the complementarity problem. We need x in capital X, f of x in the dual cone x star, and we need x and f of x to be perpendicular. So if I want to show that f of x lies in x star, that's equivalent to saying y transpose f of x is non-negative for all y in x. It's could you repeat your name? Stefan, sorry. So do you agree? That's just the definition of the dual cone. Okay. So now remember that we have this. Why do we have this? We have this because we know that x solves the Vi. Do you agree? So then I can take this part to the right side. So, but I know that I've proved complementarity, so I know this is equal to 0. So I just proved that. I proved x and f of x are perpendicular to each other. Right? Here. And so, this implies y transpose f of x is greater than 0. Is that clear? Okay. Okay. Okay, let's go the other direction. Suppose x lies in CPX, in the solution set of CPXF. Then we know that x lies in x transpose f of x is 0, and f of x lies in x star. Right? And now all I need to show is that y minus x transpose f of x is non-negative. But that's not too difficult to do, right? Because all I need to do then so I know that x lies in x, f of x lies in x star, and x transpose f of x is 0. Right? So then all I need to show this. I need to show that x satisfies this property for all y in x. Agreed? But look at this. This is just y transpose f of x minus x transpose f of x. What do we know about this? This is 0. You get y transpose f of x. But what do we know about y transpose f of x? We know where does f of x lie? In the dual cone, right? Because it lies in the dual cone, this is always greater than 0. We get our requirement. Okay? So that allows us to go in each direction. Okay? Now, so now what we did was we spent time looking at VIXF and just showing you the equivalent equation reformulation. Now I'm going to a special class of VIXF, which is the linear complementarity problem. And the reason why I want to talk about the linear complementarity problem is because it captures a fairly important class of Nash games, namely bimatrix games, which I talked about yesterday and I'll talk about today, quadratic Nash games like Cournot games. And you can get the existence uniqueness results often just by using optimization theory directly. Okay? So let's consider the unconstrained convex quadratic program, okay, given by half x transpose mx plus q transpose x, where x is non-negative. Whenever I put something in brackets here, this represents the Lagrange multipliers. Okay, so it's u is a Lagrange multiplier corresponding to the inequality constraint, okay, or the dual variable. Okay, M is going to be assumed to be an n by n matrix, and it's just for this discussion, it's positive semi-definite. Okay. Now the sufficient conditions of optimality. I want to make sure that everybody, before they leave this course, we are familiar with how to get optimality conditions. So if I have a problem like this, so if you look at the way this problem is, you just have, okay. So the general way we do it, and you'll get used to this, is write out the Lagrangian function. Okay. Now I'm going to differentiate the Lagrangian function and set that derivative to be 0. Right? What else do I have? I have a complementarity relationship between u and x. Right? That's part of the statement of the optimality conditions. Now, from this I have that u is equal to what? Mx plus q So I can eliminate u, and I just get mx plus q is orthogonal to x. Okay. Now this is referred to as the linear complementarity problem m comma q. Because look at it, it's basically a complementarity problem where the mapping f of x is just mx plus q. Okay. So now what you have, now the reason why I wanted to stick with positive semi-definiteness is because these conditions are now necessary and sufficient. Okay. So now I've got this set of optimality conditions. It turns out the optimality conditions are precisely the linear complementarity problem that I'm interested in. Okay. And this, the LCP problem, is to determine an x such that x is non-negative, mx plus q is non-negative, and x and mx plus q are orthogonal. Okay. Now you can also write this, you can also write the same problem as a VI, right? So this is something I want you to get used to. You need to be able to traverse between these two objects without too much difficulty, right? And that's why I will keep going through this in class and keep kind of making sure that you can write these. So if I gave you an optimization problem like this, what is the VI representation of the necessary and sufficient conditions? So this is the set, this is the objective. So the variational inequality is just the set, which is Rn plus, and the gradient of this objective. What is the gradient of this objective? Mx plus q. Right? Remember, this problem is equivalent, as we showed, to this problem, LCP MQ in this case. Right? We showed that, the previous result. Right? We said if x is a solution of this, it's a solution of this, or because the set is a cone. In this case, it's a cone. And this problem is just mx plus q transpose y minus x. So this is all y in x, but this is just y in non-negative because x is a non-negative. There's a non-negative ortho. Okay, so that's the variational inequality problem. So every convex QP of this form, QP is quadratic program, sufficient optimality conditions will be written as either a complementarity problem or a VI. And in fact, any convex QP may be recast as a mixed LCP. I don't do mixed LCPs much in this class, but let me just tell you what they are so that you understand how to deal with them. Suppose I had an AX equals B here. And if I wanted to write down the complementarity conditions or the necessary and sufficient conditions, how would I proceed? I would say the Lagrangian function would be, so if this is u and this is lambda, you get half x transpose mx plus q transpose x minus lambda transpose ax minus b minus x transpose u. Okay. So now I take the gradient of the Lagrangian in in x, and you get mx plus q minus a transpose lambda minus u, and you have a requirement that ax has to be equal to b, and you have x is orthogonal to u. Remember, u can be eliminated from here, so this is equal to 0. U is equal to mx plus q minus a transpose lambda, which means that I can write this as mx plus q minus a transpose lambda. And I have a complementarity condition here between, this is, this is fine. So this is the mixed LCP. Okay, it's a mixed LCP. And the lambda can have any sign. find an x such that ax equals b and x is orthogonal to this. So you want an x and a lambda that satisfies this. Yes? Mixed because you have an equality constraint sitting there. Okay? A pure complementarity problem only has inequality constraints. A pure complementarity problem can be written as just x lying in a cone, f of x lying in this dual, and x and f of x being. You can actually look at this. So can someone tell me how I can rewrite this? Oh, so this was an exercise question which maybe we can do right now. How would I write this? So Priyanka asked the question. So maybe Priyanka can answer the question. How would I write this as a pure complementary problem?
Can you add some slack variable to that equality?
No, if you add a slack variable, so if you add a slack variable, then the issue becomes you need to make sure that slack variable has to be 0, right? So you have to be a little careful about that. So you can't do that. What else could you do? But you're in the right direction. So what is ax minus b complementary to? So what is ax minus b equal to? Somebody else asked me this question yesterday. Was it Arno? I don't remember. You said, so if ax minus b is equal to 0, what is the dual of cone associated with 0? So if I tell you x is just 0, not the empty set, 0, it's a singleton. Go on, Olivia, you got it? It's Rn, right? So now if it's Rn, so what we can write this as ax minus b is in 0, right? And this is orthogonal to lambda, which lies in Rn, because lambda does not have a requirement in terms of sign. So then you can write the x in Rn plus, and you have mx plus q minus A transpose lambda. This is also Rn plus. So now you can write this whole thing as z lying in some larger cone, which is the Cartesian product of Rn times Rn plus, orthogonal to this, which is some f of x lambda. Actually, you can write it like this. M minus A transpose A 0 x lambda plus q minus b lying in x star. Okay? So you can write it as a pure complementarity problem, but so can someone tell me why I'm interested in keeping it separate? That's actually an unfair question. So the reason we're actually interested is not from a mathematical standpoint, it's more from a computational standpoint. If I know that I have equality constraints, often in an optimization setting, if I have some structure, I might be able to eliminate these. I might be able to work in the subspace of these. So there's a reason that I want to keep them separate and explicit. So algorithms often use that structure. Okay, so yeah. Okay, so remember, not every LCP can be viewed as the optimality conditions of QP. Here we wrote it as, oh look, this LCP represents the optimality conditions of a QP. But what was crucial in this? What did the M have to be for this to happen? It had to be symmetric, right? It had to be symmetric. Now you might say, well, you wrote this could have just been some arbitrary matrix. Well, if it's an arbitrary matrix, what happens in the optimality conditions? What happens in the optimality conditions if the M that I gave you at the outset wasn't symmetric? What happens when you differentiate a quadratic function where the inner matrix is not symmetric? Well, what happens is, just from so if I gave you this, so if I gave you a function like this, I said, suppose I gave you this function, and I tell you differentiate this function. What rule do you use to differentiate this function? The chain rule, right? So you'd use basically something like you differentiate this times this, this times this, right? Now, essentially, let's do the same thing here. If you differentiate this, right, what you're going to get is M. Go the other way, you're going to get M transpose. So whenever you work with matrices which are not symmetric, the gradient for that matrix, for that system will always be the symmetrized version. What is the symmetrized version? Just M plus M transpose divided by 2. So it'll be twice the symmetrized version. Okay? And but then you come to this conclusion that, is it true that every time I have an LCP, it comes from the optimality conditions? It cannot, right? Because unless the LCP is only has symmetric matrices, that can't happen. So it's much more general than that. The only reason I do it here is it motivates it. Okay? We require that the M be symmetric for it to be viewed as the optimality conditions.
Whenever you can have break.
Oh, yeah, okay. So we can stop because this is now I'm going to the feasibility and solvability.
I had one quick question.
Yeah, yeah.
On the definition of the VI for LCP.
Yeah.
Here. So is there a specific reason why you made it Rn instead of Rn plus?
Oh, no. This is a typo. Sorry. It's Rn plus. Sorry.
Yeah, I can have another question.
Yeah.
So in definition of VI, we had conditions of convexity and closed, being closed set.
For the set, yes.
For the set. But here in the last example, we
Because
don't have
it's
closed.
the non-negative
So it should be
orthant is,
closed just from one side.
well, the non-negative orthant is basically considered open and closed.
Okay.
So, and, but from our standpoint, it's a closed set, and it's a convex set. So this trivially holds. But remember, in the case of this, so that's exactly, yeah. And remember, when I'm looking at the CP version, I'm just needed to be a cone. So if it's it's a non-negative orthant, it's a cone.
So to have them equivalent, we need to have the set as the cone, otherwise.
Yes. If the set is in a cone, you can't do it. Okay.